Okay, so we're going to talk a little bit about properties of waves. They are disturbances in a medium of some sort. Most waves require a medium, and mechanical are the ones that do. Electromagnetic is the exception. That's things like the sunlight that comes through the vacuum of space that we get bathed in every single day. Multiple types of waves. The pulse wave is just that single pulse traveling. You did that with the waves out in the hallway during the lab. A periodic wave is where we have some periodic disturbance, like this line, that spring going up and down and up and down. So you get a series of pulses. And a sine wave is just a special periodic wave. We've got a simulator that we're looking at here. So if you are missing these notes and you're listening to this on YouTube, you'll need to check out the string simulator. You can even download it for your phone. Actually, you can have hours of entertainment playing with the string simulator, making waves on your phone and not talking to other humans, which, wouldn't that be great to socially isolate yourself for the sake of physics? No. So a sine wave is just a special periodic wave. Now, within the two big subsets, mechanical and electromagnetic, there are also subsets. And transverse waves are these guys. They're what you've always thought of as a wave. So we can measure things about transverse waves. And, you know, these are the crests of the waves, the top parts. These are the troughs down here, these bottoms. And one wavelength is one entire cycle of motion. So one wavelength involves going from a trough to a trough or a crest to a crest. That is one wavelength. The one you want to be careful about is going from equilibrium to equilibrium. Because if you go from the equilibrium position to the equilibrium position, this is not a wavelength. Why? You've only gone through half a cycle of motion. So to get a wavelength going from equilibrium to equilibrium, and this is a really common mistake, which is why I'm pointing it out, you have to go all the way through, so the second time you hit equilibrium is actually a full cycle of motion. So it's much easier to just go crest to crest or trough to trough. Okay, you're less prone to mistakes that way. And wavelength is given by the Greek letter lambda. You probably did a little bit with lambda in chemistry when we were talking about electromagnetic waves, but not a lot. The other kind of mechanical wave is a longitudinal wave. This sometimes gets called a compression wave. In this, the vibration of the particles is parallel to the motion. So back here, the vibration of these particles is perpendicular to the motion of the disturbance. So the disturbance is traveling this way, the particles are traveling up and down. In a compression wave, the disturbance is traveling this way and the particles are traveling back and forth. Okay? So the motion of the individual particles is in the same plane as the motion of the wave itself. This is a slinky. This is a slinky wave. And many people actually think of them as slinky waves. So instead of crests and troughs here, we have compressions and rarefactions. Okay, so that'll be it, I guess, since all seniors are returning to the auditorium, and have a good weekend. We'll see you Monday.